So, hello everyone. My talk will be on working title More Neurons or More Complex Neurons by me, Georg, Matheus, Anna Levina, who's sitting here. And I will introduce the question first. So, if you think of neural systems, in particular, if you look at the human brain, you will find cortical neuron. And it seems they're surprisingly complex to what people typically assume. So, they have many branches, single output maybe, many hidden states, and with lots of internal processes that develop over time. And then there's something happening there which is integrating all the information over the branches. And there are many nonlinearities, and anyone who did computational neuroscience knows, I mean, there's a tons of nonlinearity and complexity in there. But actually, this is typically not modeled. But it motivates why you might want to look at whether you actually should model this. And also in deep learning, typically use like a perceptron, so like a linear weighted sum of your inputs, and that's about it. I mean, if you think maybe of transformers with like multi-head, then you might get an inkling of why modules of complex information processing might make sense. But let's leave it here at that. And then the next step is, of course, the cortex, which assembles these millions or billions of potentially complex neurons into a layer, somehow connected. And maybe one observation that is maybe curious, if you know or don't, that anatomically these cortices look very flat. So there's maybe like 6, 7 layers, but they're incredibly wide. And then the connectivity does the rest of the structure. And then finally, the question would be, okay, let's say you have a resource budget or like a fixed resource budget. Like, I mean, in nature, you don't get to have as much as you want. You basically operate under constraints. And the question is, if you have a fixed budget, how should you allocate this budget if you were able to? Like, should you put all of your budget into like as many neurons as you possibly can, but make them very simple, whatever that means? Or should you rather take a few of them, but make them super complex and connect them somehow, and maybe this somehow translates into some downstream performance of your task or survival or whatever. And then you could even look at the scaling laws of this, like if I decide to do many small ones, my system scales such and such with the budget, or you do it otherwise, like maybe few neurons, but you make them always complex, and then how do you allocate the budget? What is giving you the best scaling laws? And basically, I'll talk about how we approach this question, and then I'll talk about our findings. And in the last paper, which was already like ages ago, we developed a single neuron model that sort of tries to capture this complexity of single cortical neuron in a bunch of ways, but just roughly, I mean, you have some inputs, then you have some branches, then you have a nonlinear transformation on this. This goes into a hidden state, like we could call it memory units. These memory units are basically a hidden state over time. So this plus your input at every time step gets integrated, potentially, highly nonlinearly, into your memory units, your hidden state, which is then read out in some simple way. And then this publication, or in our submission that I'm working on for Neurons now, there's some bit of addition, which is non-trivial, but like there's a high-pass filter on the memory units before they get sort of sent out as a single scalar, potentially binary value as the output of the neuron. And then you take a whole bunch of these. I mean, I'm looking at two-layered architectures primarily. The ablations that you will see are about the hidden layer, and this hidden layer is then our object of investigation. Like, do we make it super wide or a bit less wide, but the individual neurons much more complex, and what is going on? Also, it is a recurrent network, so I mean each neuron is recurrent, but then we're crazy and we put each of these recurrent units in a whole ass recurrence. So it's like a recurrence of recurrence. but it works. So we kind of spent a lot of time like mitigating, vanishing, exploding gradients. Also, I talked a lot to Antonio, so we talked a lot and had fun. And this is about a single neuron that is an RNN, and now this is an RNN of RNNs. And yeah, this is the question, like how should you make this unit? Like, should you make it big, small, wide? And then there are other architectural choices. The two ones that we'll talk about today is the number of neurons and complexity, but you could talk about connectivity. And actually, I might talk about connectivity now after all, and recurrence. Yes. Okay, and this is what now we're talking about the scaling as in trade-off. And the first two graphs are what you would expect and see and know and love about deep learning. Like you improve your network along one dimension, like in this case, like you give it just more neurons. Like we're talking about a fixed, everything else is fixed hyperparameters. Your training, your everything. Also about the architecture, but you give it more neurons. More neurons, better performance, cool. More complex neurons, better performance, cool. Like this, you've seen a million graphs like this. Nothing interesting about this. This is where it gets interesting. Now we assume a fixed budget. Whatever, like each line corresponds to a fixed parameter budget, like whatever. In this case, it is parameter budget. And what you get is suddenly you get a trade-off. Like now it's not just more is better. Now there is a particular combination of your complexity and number of neurons that performs best. And it's a non-trivial one. Like it could have been like, oh, just give it as many neurons as possible and don't care about the rest. Then you would have gotten like a slope declining like this, right? It would be like just as many neurons as possible. Or the other direction would be like homogeneous blob. Like like there was some hypothesis about the brain. I learned today that the brain was a blob, is a blob, and then you would get like single neuron, make it as big as possible, done. But no, this is not the case. Like you get a non-trivial optimum, and the question is, of course, why there? Why not here? Why not there? And interestingly enough, like if you double the budget or halve the budget, so you change your budget, this optimum shifts. For example, if I halve the budget, I mean, here it's hard to say. Okay, we'll look at other plots. Okay, like if we increase the budget, it seems like suddenly more neurons are better, but not only more neurons, but if you believe me, also more complex neurons. Here it's easier to see. Overall, the pattern is more budget, more neurons, and more complex neurons, and it's not quite clear how exactly should the trade-off be, but it's roughly this. Like the more budget you have, it's not just that you should make more neurons, you should make them also more complex, which is, I think, a pretty cool finding. Like this is the main finding. So it's not more or more complex, it's both. It's more and more complex, and it depends on your budget. I don't know what the time is, but I'm hurrying up. And then we supplemented this with a theoretical modeling approach based on information theory, where I derive, or we derive, I mean, it's not that big of a derivation. There's a formula in the end, which sort of, I mean, this is the experiment we saw before, just extended for more runs. And you here see it also more clearly, that sort of more budget, you should make more and more complex neurons. And now we have also an analytic formula that basically reproduces these qualitative changes and shows you exactly, based on how well your assumptions hold in your particular architecture, how you should allocate budget. Like how exactly should you increase your budget, my bad, the number of neurons and the complexity of neurons if you get this and this more budget. There are other hyperparameters of the theory, which relates to exactly how well does, if you have a single neuron, performance increase if you have a single neuron. Like just like you fit a single neuron to reproduce the input-output relationship of another single neuron, and you have this, and you ask yourself, okay, how well does it do it? And you could say, okay, it does it enough. Doesn't matter. But it relates to this as well, and the eigenvalue spectrum of your activations in the hidden layer. Anyways, two other things. So for the same set of parameters, we reproduce these qualitative changes in optima and also for other parameters, such that basically, depending on how well the assumptions hold for your network, you could predict how performance improves across orders of magnitude, like whatever. Yeah, and that's basically it.